Hello everyone, welcome back to this lesson of probability. We're still looking at our types of events, and the next type of events we are going to look at is the mutually exclusive events. So two events A and B are said to be mutually exclusive if they cannot occur together at the same time. So here you have your two events, but those two events cannot occur together at the same time. For example, if I'm to give a real life example, you cannot have light and darkness at the same time under normal conditions. It's either light or darkness. You don't have anything like an intersection. Other examples, you cannot pass and fail at the same time. So you either pass or fail. There's nothing like an intersection. So that's what we call mutually exclusive events. And the condition for mutually exclusive events is that they don't have an intersection. Why? They cannot coexist, or they cannot occur together at the same time. And this is the condition. Probability of the intersection B is equal to 0. That's the condition for mutually exclusive events. We should remember that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. But for this type of events that we are talking about, the mutually exclusive events, since they don't have an intersection, so for mutually exclusive events, since they don't have an intersection, it means that probability of A union B will be equal to probability of A plus probability of B minus 0. And therefore, the condition for mutually exclusive events concerning their union is that probability of A union B is equal to probability of A plus probability of B. That's our condition for mutually exclusive events. We shall look at some numeric examples concerning the mutually exclusive events, and we shall see how we apply these conditions. So the first example says events A and B are mutually exclusive, so they will always tell you the type of events. The events are mutually exclusive. Mutually exclusive, we shouldn't forget, it means that the intersection doesn't exist. In other words, probability of the intersection B is equal to 0, such that probability of B is equal to a half and probability of A is equal to 2 out of 5. But A wants us to find probability of A union B. So in order for mutually exclusive events, probability of A union B is just probability of A plus probability of B, since they don't have an intersection. So by substituting, we shall have 2 out of 5 plus a half, which will give us 0.9 as our value of probability of A union B. Part B wants us to find probability of A only. Probability of B only, or probability of A complement intersection B. So that value is got by getting probability of B minus probability of A intersection B. But what is our probability of B? Probability of B is a half, and probability of A intersection B is always 0. So we shall end up with probability of A complement intersection B as a half. Then part C wanted us to find probability of A complement intersection B complement. So from De Morgan's rules, we know that probability of A complement intersection B complement is actually equal to probability of A union B but complement. What we do is that we factor out the complement and the sign here. The intersection changes to union. So that value will actually be equal to 1 minus probability of A union B. This is what this means. But probability of A union B, we got it in Roman 1 as 0.9. So we shall end up with our probability of A complement intersection B complement as 0.1. Then in our second example, we are given events A and B that are mutually exclusive This condition is very important. It means that the intersection doesn't exist, such that probability of A union B is equal to 7 out of 10 and probability of A is equal to 3 out of 5. That has to find the value of probability of B. So we shall use the information we've been given to find the probabilities we don't have. We know that probability of A union B for mutually exclusive events is actually equal to probability of A plus probability of B. But by substituting, we shall have 7 out of 10 being equal to probability of A, which is 3 out of 5, plus probability of B, which we are looking for. And when we solve that, we shall get our probability of B as 1 out of 10. Then part B wanted us to find the value of probability of A complement intersection B, or probability of B only. We know that probability is got by getting probability of B minus probability of A intersection B. We looked at that in our first lessons. But what is our probability of B? Our probability of B is 1 out of 10, and our intersection doesn't exist for mutually exclusive events. So we shall have our probability of A complement intersection B as 1 out of 10. Then part C wanted us to find the value of probability of A intersection B complement, or probability of A only. So we know that value is got by getting the probability of the entire set A minus the intersection. But we are given probability of A as 3 out of 5, and probability of A intersection B doesn't exist since these are mutually exclusive events. So we shall end up with our probability of A intersection B complement as 3 out of 5. Then part D wanted us to find probability of A complement intersection B complement. So we looked at that case where we can apply De Morgan's rule by factoring out the complements that are appearing on those values. So we can factor out those complements and the intersection changes to union. But we know that this A union B but complement is the same as 1 minus probability of A union B. We looked at that condition under complement of events. So we shall have 1 minus probability of A union B, which was given to us as 7 out of 10. And when we solve for that, we shall end up with probability of A complement intersection B complement as 3 out of 10. Then part F wanted us to find probability of A union B but complement. I told you how to find these probabilities. You can first quote the formula for finding probability of A union B. It is probability of A plus probability of B minus probability of A intersection B. But since this time we have a complement on the B, we shall end up putting it wherever B appears. So we shall put a complement there, a complement here, and a complement here. And therefore we shall end up having that as our formula for probability of A union B but complement. So by substituting, I have my probability of A as 3 out of 5. I got my probability of B as 1 out of 10. But they want the complement, so it will be 1 minus 1 out of 10 minus probability of A intersection B complement, which I got as 3 out of 5. So I will solve for that, and I'll end up with 9 out of 10 as my answer to the question. So probability of A union B but complement is actually equal to 9 out of 10. Yes, so we shall end this lesson at that. In the next lesson, we shall look at more examples that are showing us how we can apply the condition for mutually exclusive events. Thank you very much. Let us meet in the next lesson.